Dear world, welcome back to the topological sorting. So in today's video, we'll be understanding the topological sorting. Then we'll understand the concept in very depth, in very deep wise. And then from the diagrams, we'll convert that concept, that diagram into code section. So without further wasting time, let's move to the topological sorting session. So first, let's try to understand what is this topological sorting. So we can call it that the topological sorting is a special case of DFS. Exactly. This topological sorting is nothing but a special case, a special application of DFS. So let's study what it tells about the topological sorting. That topological sorting is the linear ordering of vertices in a directed acyclic graph. So notice the two most important factors here. The first one is directed, and the second one is acyclic graph. That means topological sorting is nothing but a linear ordering. That means it's a ordering in linear wise. That means that is a linear, that is a linear, that is a linear, and that is a linear. Can you see the linear relationship? Linear. So the question, that is it a topological sorting? Is it topological? Is it topological sorting? The answer is no. The answer is big no. You might be thinking why this is linear. Look, first of all, it must have a direction. The first important point it tells that it must be directed. So okay, it is satisfying that it is having a direction. That is having a direction. But the second point, a cyclic graph. Look, this point, this is a cyclic graph. That means no cycles. That means for topological sorting to be constructed, to be occur in any graph, there should not be cycles. So if you get a graph like this where there is cycle, we cannot see any topological sorting. We should have no graph. So let's say the example, this one, the small example. We have a point A to C and another point A to D. So first understand what is the meaning of A to C and A to D. A to C and A to D, that means if A, here A is before C and in the next case A is before D. So that means A must come before C and D in every case. A must come, that means before C and D. It waters node such that for every directed edge u to v, u node must come before v in the watering. So that is the case that whenever there is, we have to consider this first element. This first element will always come, will always get the first preference. That means how we can make it a graph, then it will be like this. We can represent the graph like this. A will be at the first position, it is always prior, and then after A it comes to B, C, and this relationship number 1 is done, and now it is pointing to D. This type of directed and acyclic, that is no cycle, that type of representation is topological sorting. Performing this topological sorting, we create that type of sorting, and that is topological sorting. So the important case might be that why do we study topological sorting? So the funny answer is because this is in the book. Okay, that is in the book because in real life we see the applications of topological sorting. So let's check the applications of topological sorting. So what it tells, let's have a little bit more look. Topological sorting in a linear ordering of vertices in a directed acyclic graph. It orders nodes such that for every directed edge u to v, node u comes before v. So it is telling the same thing that for every directed cycle, for every directed edge, u will come before v. That means if that is A to C, so A was always before D. So that is topological sorting. That means it should always come before everyone in the graph. Okay. Now let's understand the applications, real life application. So when do you use course scheduling? I mean the applications of topological sorting. Suppose we are course scheduling, you have a course like Java. You have a course like Java and you have a course like computer networking. You have those courses. So we want to give more preference to Java, that only after Java is proceeded, Java is accomplished, then we'll be moving towards the computer networks. That means first we'll be proceeding the Java. Once Java is done, then we'll be moving towards the computer networks. So that is the dependency, that Java is getting the higher priority. Then we move to the computer networks portion. So this is that type of directed and non-reversed acyclic relationship. We use the topological sorting. Project management, for maintaining the project. Suppose we have a project like this. We have a project where there are multiple projects and those are which are not dependent, that means independent projects. So we first complete the independent projects. and then we move towards the dependent project, package dependency resolution. So suppose you want to install some game, installing some software or game or software. So there are few required packages that must be installed, that must be installed prior to the software is installed. So that is given higher priority, and that is also an application case of this topological sorting. Compiling order, this is very much easy. Let's say this is topological sort. So this is, there is a function topological sort, and this function is dependent on another function. That means it is calling inside another function, topological sort util. It is calling this helper function. So who is independent? Topological sort util is independent function. Topological sort util is independent function here, and that's why first this will get the priority. Once this is executed, then again program control will back to this is also performed using topological sort. So we understood about topological sort. Now let's try to understand in more depth with an example. Look, you can see edges. These are the edges. So first let's see how we represent the edges. So these are edges. So when we implement the graph, you can see here, this is a graph. The things you can see here, that is a graph. That is a graph. So we implement this graph either using adjacency list or adjacency matrix. So how we represent the adjacency list? Like this. First we will be having nodes, and then that will have a list. First we'll be having nodes, and after the nodes, it will have the directed relations neighbors of the nodes, as we genuinely have. So look, we have A, as you can see, and now A will have a neighbor A to C and A to D. So A is having a neighbor A to C and A to D, so we'll be including C and D. Second, for the node B, we can see from here that for the node B, D and E. Now for the node C, the neighbors are F. For the node D, the neighbors are F and G. For the node DE, the neighbor is H, and for the node F, the neighbor is also H, and for the node G, the neighbor is also H. So now notice one important thing to notice here. If you see for the node G, but again if you try to find for node H is also class, no? Okay. So that is our graph, and now let's try to understand in more details. That is, now we have H, and what we have seen in previously, that if G is connected to H, so with respect to H, can you provide G? In normal adjacency list, you have provided that if G was the neighbor of H, so similarly H was also the back neighbor of G, but in topological sorting, H will be empty. H will be empty. That means H will have no. Why? Because in topological sorting directed, the relationships are directed, that is from 1 to 1. The relationship is from A to B, but the relationship is not from B to A. This is not the relation in topological sorting. That is, we have to keep in mind, that is one way directed, and that is the main things of topological sorting, that everything we see here, that is one way directed. One way directed. And if that was possible, that it is moving to this and it was again moving back, so look, there is cycle is possible here. It is coming here and then again it is moving where, so it has a cycle. So this cycle is not possible. When we just remove this cycle from DFS, it becomes the topological sorting, because in DFS we can see those cycles, but in topological sorting this is a special next level case of DFS, so then it becomes the topological sorting. Now let's see the implementation. Now A is actually dependent on two factors. You can see this is C and D. So now look, A is pointing to C and D. Similarly, B is also pointing, A and B both are pointing to D. So B is pointing to D and B is pointing to E. That is the easy graph. Now C is pointing to F. So we have created a IF node and C is pointing to this F node. D is pointing to F and G. So D is pointing to F and D is pointing to G. As it is working, now E is pointing to H. So this is our H node and E is being pointing to H node. G is also pointing to this node and F is also pointing to this node. So all are pointing to this node, and by this we have constructed all the graphs. So in topological sort, if we just sort, if we perform sort, how can we visit this? will be visiting like this. Will be first, they come at the foremost position, that is topmost position. So we'll be visiting those two first. So it will be like this. First we'll be visiting AB. Once we have visited AB, then only we'll be visiting Doge, CDE, level by level. I mean that type, similar of that type, but not exactly that type, because we can also shuffle those. We can also shuffle those. Sometimes it can be forward, it can be go backward, then and then the next level G comes, then G, and then AFH. So it will have a special kind that you will be seeing through the codes. And so let's start understanding this with the help of class. So first what we'll be doing, we'll be just creating a class. So let's start by making a class. First you can see the graph. This is graph. So whenever we start a program, we first write the class file. So we'll be creating this graph for performing topological sort. So let's start, and we'll be calling it class graph. Class graph. And now we are starting the class. First what we need to do, we need to count the number of vertices, 1 2 3 4 5 6. So we have to pass the number of vertices. So we will be passing like private integer number of vertices. This is because the number of vertices with which we want to create the adjacency graph. Next we'll be creating a adjacency list. So private, and we'll be creating the adjacency list with respect to array list, because array list is more memory efficient, more optimized than linked list. If we only need frequency insertion deletion, then we utilize the linked list, but in general case we'll be using array list because it is more optimized. So we'll be simply implementing private list, and this list will be storing list of type integer, and we call it adjacency list, as always we have been calling. So now we call it adjacency list. Now we will be calling the constructor class. So let's call the constructor class, and there we'll be initializing the number of vertices. So public graph, public graph, this is constructor class, and we'll be passing integer number of vertices. Okay, and now we'll be initializing this dot number of vertices, this dot number of vertices, that is equals to number of vertices. Okay, so now we have initialized the number of vertices. Now we'll be initializing our adjacency list. So adjacency list aadj, that is equals to new array list, and generic type dynamic one. This is generic type dynamic one. So now we have initialized the list, and now we'll be initializing all the arrays one by one, all the array lists. So for that we'll be running a loop for integer I equals to 0, I less than number of vertices, I plus plus. Now this loop will be running, and we'll be simply adding one by one like this. Our list will be like this, and we'll be adding everything will be one. Everything will be a array list. So for that we'll be adding all the array list. So adjacency list, adjoint list dot add. Okay, this adjacency list is the name of this adjoint dot add. And now we'll be adding the new array list, new array list, and now we are adding the new array list. Okay, by now we have added the new array list, so we'll be closing this file. Okay, so now we have created the graph class. Once we have created the graph class, now we have created the graph class, and now we have allocated a graph like this. By this time we'll be having a graph like this, and it will have all those will be a array list. These are all are a array list which will be containing integer. Same, this is also array list, this is also array list. So these are all array list, and we have also initialized the number of vertices 1 2 3 4 5 6 7 8. So the number of vertices 8, that we have also initialized by the above code lines. We have initialized the number of vertices, and then we have assigned the number of vertices here. Then we have also assigned the memory for the adjoint list, and now in every index there exists one array list. So okay, now we need to add. Now we'll be implementing code for this section. That how we can add those lines. For those lines, we have to add the dot age method. For that, we have to add the dot age method. Okay. So now let's start by performing the add age method. So first we have to get the vertices whom we want to add, and then we will be adding the vertice with whom we want to add. That means we can call it, let's say this is V, that one is V, and that one is W. So we want to add V to W. So for that, let's write the function public void add age integer V comma integer W. Integer V and integer W. Now we'll be getting the V, that is adjacency list, that is adjacency list dot get of V dot add of W, adjacency list dot get of V. First we are getting the V, whatever the vertices, input vertices, then add of W, then it is pointing towards the W, that means V is pointing towards the W. We have done this line. Now we'll be performing the topological sort function. So let's start performing this function. And for that, first we'll be calling actually the topological sort function, and so we'll be writing the topological sort function. And while we write the topological sort function, we'll be using a stack. We'll be using a stack. In topological function internally, we'll be using this stack, and we'll be using visited, shared. Those are the two most important things that we'll be using to perform the function. So let's write the function public void public list of integer, that will be returning a list filled with integer. Topological sort. So now we'll be start performing the topological sort. So first what we'll be doing, we'll be initializing this stack. So stack, and we'll be initializing this stack with respect to array dq. So new array dq, we'll be calling this new array dq. So new array dq. Okay, so now we have initialized with respect to array dq. Now after that we'll need to initialize this set visited, set visited, what will be tracking which have been visited. So for that we can either use set or either with boolean. So let's use boolean for more memory efficiency. Boolean visited, that is equals to new, and we will be allocating memory for all the number of vertices that are present. So new boolean, and we'll be allocating memory for all number of vertices. So by now we have allocated memory for all the number of vertices. So now the next line is we have to perform DFS for all unvisited. If that is not visited, we have to perform DFS. If that is not visited, we have to perform DFS. And for that, we'll be utilizing our topological sort util function. So let's write it. So now we'll be performing DFS for all unvisited vertices. So we'll be writing like this. We'll be using a for loop for integer I equals to 0, I less than number of vertices, and I plus plus. And now we'll be checking if those are not visited, if not of visited of I, if that index is not of visited, then we'll be applying DFS method, that is topological sort util method. It is nothing but all similar like this topological sort util method, and we'll be calling this util method with respect to the current index. We'll be passing our visited array where we track and the stack also, and then this. After this entire program is executed, we will be retrieving the topological sort. Now retrieving. Now after while program is executed, retrieving the topological sort. So for retrieving the topological sort, we'll again write few lines. So simply just we will first create a topological sort variable. So list of integer topological sort, and now we'll be retrieving with respect to array list, new array list with respect to the values of stack, and now it will be creating a new topological sort, and you will be simply returning this topological sorted order. So return, we can also call it topological order, return topological order. Okay, so now one thing that we have called the topological sort util, this function that we have called, and that is the main function. That is the main function where we perform all the DFS logic. So let's implement this topological sort util function, and that function returns I think nothing. It just internally changes everything. So private, internal methods are always declared as private. So void private void topological sort util, topological, and we pass the array index I, then we pass now we have to define with type integer v boolean, and the name was boolean visited, and we made an array of type dq where we stored dq integer of stack. Okay, so this is a stack. Now whoever the node comes will be mark that node as visited. That means visited of visited of v, I mean whoever the node comes will be marking. So here this is integer v, so visited of v, so this is marked at true. Or if you would use set, we could directly add also, so visited of v true. Now we'll be checking all the adjacent vertices. So for integer neighbor in adjacency of v, we'll be checking if that's not visited, that is if not of visited of neighbor, if not of visited of neighbor. If the neighbor is not visited, then again we'll be performing recursively the same function, topological sort util topological, and we'll be passing the neighbor, we'll be passing the visited array, and then we'll be passing the stack at the same condition, and recursively it will be again. And then at the end, once this node, suppose this node is entirely processed, it's this child both are visited, now we'll be pushing this node into the stack, we'll be pushing that node into the stack. So simply we'll be writing stack.push of v, stack.push of v. So by now we have pushed the stack into we have pushed the vertices v into the stack. So after all the function has been executed, now we'll be writing the driver function, the main function. So let's write the main function. So public study void main, public static void main, and it will be string args. Okay, and now we'll be creating an object with respect to the graph. So we have implemented the class using graph. So let's create object graph g, that is equals to new graph, and with respect to g, now we have to pass a construct initial as in variable 6, else we will getting error. So here 1 2 3 4 5 6 7 8, here is 8, so we'll be passing 8, new graph 8. Now we'll be adding the vertices one by n. So g dot add age. So now if we actually, here we have used character, so let's say instead of character, here was vertices 1, here was vertices let's use another color. Here was vertices 1 2 3 4 5 6 7 8. Then we could add like this, g dot add age 1 to 2, then g dot add age, g dot add age. Now this has been added 1 to 3, 1 to 3, then g dot add age 4 to 3, g dot add age 4 to 3, then 4 to 5, g dot add age 4 to 5. g.add age 4 to 5. So by this way, we could add all the ages one by one, and at the end, we could just perform the topological sort. So we could call the function like this: list of integer, because we return list of integer. Topological sort, topological sort, and we'll be calling the topological sort function with respect to the object g dot topological sort, and we don't need to pass an argument as we have no argument. So topological sort, and now this is done, the program is executed. So if we just run the program, it will provide us all the answer in the code and the topological sorting. So let's run the program in the VS Code and let's see how it works. So let me turn on the VS Code. So let's recap of the concept, what it does. It actually creates an array. Now if we just revisit entire one, so first we have declared the number of vertices. If you just see number of vertices, first we have just initialized this graph, nothing special, and then we added all those edges one by one, and then we started performing the topological sort. So when we started performing the topological sort, important things that we have created a stack. That means the stack you can see here was created. This stack was created using this line. Using this line, the stack was created. And the Boolean array, this was also created in the topological sort. Now in topological sort, for all the vertices, for all the vertices that are present here, we are checking if all those vertices that are present here are visited or not. If they're not visited, if suppose A is visited, C is visited, D is visited, but E is not visited, then we apply the topological sort util function on E. So we then come to the E. So for E, when we come to the topological sort util function, we actually check all the adjacency list. So it's adjacency list one having age. So we first process this age. We now process that age with respect to again topological sort util function. And when age is processed, that means that is also visited, and nobody is there left to visit. We add this E into the stack. Then E is added into the stack, and when all those are added into the stack, A, E, B, at the end, we are copying the entire stack into our topological sort function. As you can see, we have marked as true, and then for all the neighbors of that node we have performed this function, and at the end when it has been done, we have pushed that into stack. Topological short command yt topological sort, and now we'll be creating the file name java. So code graph.java, and we'll be removing this package portion because we don't want any package. So let's import. Okay, so public class graph. So what we need to create first in here, first we need to create adjacency list, and we also need to declare the number of vertices that we are going to use. So let's private integer number of vertices. Okay, after the number of vertices, now we'll be need adjacency list. Private, we'll be using list of list, that will be storing integer, and we'll be name that list adjacency list. Okay, now we'll be initializing all those inside constructor. So public graph, and we'll be passing the integer number of vertices. Okay, and now we'll be initializing the adjacency list. So we can initialize the adjacency list using the dynamic method. So for that, first we'll be initializing with respect to, we'll be initializing adjacency list new array list. Okay, so this is dynamic initialization, and for all the number of vertices v, and now we'll be initializing all places of it for integer I equals to 0, I less than number of vertices I plus plus. Okay, and now we'll be adding adjacency list dot add, and now we'll be adding a new array list for all positions. Okay, so we have initialized everything. Now we need to add a method of addEdge, public void addEdge. Unlike DFS where the adding age was in both directions, here we have only in one direction. So integer v comma integer w, so only in one direction. So we need to get adjacency list dot, first will be extracting for v, and whatever the list we get, array list we get, with that array list will be adding v. So add of v. Okay, so we have added the addEdge. Now we'll be performing the topological sort. So public will be returning list of integer topological sort, okay. So we are performing the topological sort. And first what we do in the topological sort, first we create a stack. So let's create a stack where we'll be storing integer stack, and now new array dq will be implementing with respect to this array dq function. So now we have created the topological sort. We'll be creating a boolean visited or set visited, whatever you want. So let's create an array where we'll be storing boolean. It's better and it's more optimized. Boolean visited, that is equals to new boolean number of vertices. So we'll be creating only for the number of vertices. Now we'll be performing DFS for each unvisited vertex. Now performing DFS for each unvisited vertex. So now we'll be checking for all the unvisited vertex, that is for integer I equals to 0, I less than number of vertices, and I plus plus. And now we'll be check if that is not visited, that is not of visited of I. That means if for that ith index that is not true, then we'll be simply performing topological sort util function. Topological sort util function. And from here we'll be passing I index visited stack. Now we'll be retrieving the topological order from the stack once everything is done. So list of integer topological order. So we name it topological order and we initialize this new array list with respect to the stack that's constructed, because stack will contain the topological order, return topological order. Okay, now we have to perform the main DFS methods in the topological sort util method. Here what we will be doing, here we'll be checking for all the adjacency list neighbors if they all are visited, and when all are visited then we'll be adding that index and we'll be marking the first one as visited at the start. So let's write private void topological, and we call it topological sort util. So here first I is passed with, which is integer, so that is our vertex integer v. Boolean visited, one array with boolean value is passed. Dq stack declared with dq type of data, and this is passed stack. Okay, so now visited, so whatever the data first we are getting on node we are processing will be marking as true, that yes, that is visited, we have visited that. Now for integer neighbor, because we always check neighbor, for integer neighbor in adjacency list of, we will be extracting get of v and we will get the adjacency list corresponding to it, and we will check if not of visited. If that is not of visited, I mean if that neighbor is not visited, then we'll again perform the same function on that, that is topological sort util, and we'll be passing that neighbor visited stack as it is. And at the end, all processing is done, we'll be adding that one to stack, that is stack dot push of v, and it will provide us the answer that we want. Stack dot push of v, the argument should be same. And now topological sort util, integer boolean dq I visited stack, this is a stack, and it's dq integer stack. So what's the problem here? I don't know, we'll be observing later what problem we're getting here. So let's write the main function to perform everything. So public static void main string args and now this is a graph, so let's create object graph g. And with respect to vertices, let's say we want to check for 6 vertices. Now we'll be adding integers. G dot integer, let's say we are adding 5 to g dot add age, and then we are adding 5 0, that means 5 is above 2 and 0. Then we are adding, let's say we want to add 4 0, and then we want to add 4 1 4 1, and now g dot add age. After that we want to add 2 3 and g dot add age, and then we want to add 3 1. So now we'll be starting printing system.out.print ln topological sort, and then we'll be storing all those list of integers in topological order that is equals to g.topological sort, and then we'll simply print all those vertices topological order for each element in this vertex print system.out.println system.out.print topological order. One by one all vertex will get printed vertex, and then okay, so this is, we're getting some problem in our topological sort function. So let's see, there is so much error. New array deq cannot infer. Oh sorry, we have to call it deq here also, deq integer stack. So this is the improved version of array deq, and we have some errors in the last side. I'm not finding an error. So let's run the program, and then we'll be able to find java compile minus d dot graph dot java. So for each, okay, so remove from here and now let's see, again compiling adjacency list, new array list of v, where is b, this is number of vertices, that is v, and now we'll be running the file java graph dot java, and now you'll be able to see the output, and as you can see 543210. So that's how the topological sort has been printed. So okay, for this till now we have seen all the topological sorting, how we perform, how direction is very important in topological sorting. We have observed all the things. So in the next lesson we'll be studying the, yeah, we'll be studying the shortest path algorithm. So okay, do subscribe and let's meet in the next lesson.